Hello and welcome back. Today we will continue our discussion on continuous time signals and systems by looking at lecture 5-3 on properties of Fourier transforms. The objectives are to review useful properties of Fourier transforms and to provide examples of solving Fourier transforms using properties. The first property we will examine is linearity. Suppose x1 of j omega is equal to the Fourier transform of x1 of t, and x2 of j omega is equal to the Fourier transform of x2 of t, and x3 of j omega is equal to the Fourier transform of x3 of t. Let x3 of t equal a1 x1 of t plus a2 x2 of t. Find x3 of j omega. So using our definition of Fourier transforms, the first thing we'll have is x3 of j omega is equal to the integral from negative infinity to positive infinity, x3 of t, e to the negative j omega t, dt, which equals the integral from negative infinity to positive infinity, a1 x1 of t plus a2 x2 of t, e to the negative j omega t, dt. So now we're going to separate this into two integrals. The first one will be a1, the integral from negative infinity to infinity, x1 of t, e to the negative j omega t, dt, plus a2, the integral from negative infinity to infinity, x2 of t, e to the negative j omega t, dt. So finally, we would have a1 times x1 of j omega plus a2 times x2 of j omega, which shows that if x3 of t is linear, then x3 of j omega is linear, and that it obeys multiplication and addition. We can also show that if x of t is real valued, then x of j omega has Hermitian symmetry. So if x of t is real valued, this means that x of t equals x conjugate of t. So if we find x of j omega is equal to the integral from negative infinity to infinity, x of t e to the negative j omega t dt, and the conjugate of x of j omega would be the conjugate of negative infinity to infinity, x of t e to the negative j omega t dt, which can be written as the integral from negative infinity to infinity, x conjugate of t e to the j omega t dt. But since we know that x of t is real valued, then x conjugate of t equals x of t. So we have the integral from negative infinity to infinity, x of t e to the j omega t dt, which equals x of negative j omega. When x conjugate of j omega is equal to x of negative j omega, we say that x of j omega has Hermitian symmetry. And what this means is that the magnitude of x of j omega equals the magnitude of x of negative j omega. So the magnitude is even. And this also means that the angle x of j omega is equal to negative the angle of x of negative j omega. So the phase is odd. Now let's examine the time shifting property. If the Fourier transform of x of t is x of j omega, then the Fourier transform of x of t minus t naught is e to the negative j omega t naught x of j omega. Let's prove why this is true and look at a simple example. So the Fourier transform of x of t minus t naught is equal to the integral from minus infinity to positive infinity, x of t minus t naught, e to the negative j omega t dt. And now we're going to do a variable substitution and let tau equal t minus t naught, which means that d tau is equal to dt. I can rewrite the integral as the integral from negative infinity to infinity, x of tau, e to the negative j omega times the quantity tau plus t naught d tau. I can pull out e to the negative j omega t naught and multiply that by the integral from negative infinity to infinity, x of tau, e to the negative j omega tau, d tau, which can also be written as e to the negative j omega t naught, x of j omega. So, for example, if we have x of t equal to the rect of t over 10 milli, the Fourier transform of that is x of j omega equals 10 milli over the sinc of omega 10 milli over 2 pi. So if we shift the rect and have x of t is equal to the rect of t minus 5 milli over 10 milli, then the Fourier transform is x of j omega is equal to 10 milli times the sinc of omega 10 milli over 2 pi times e to the negative j omega 5 milli. Now let's examine frequency shifting. If the Fourier transform of x of t is x of j omega, then the Fourier transform of e to the j omega naught t x of t is x of j omega minus omega naught. Let's do the proof of this and then look at a simple example. So the Fourier transform of x of t e to the j omega naught t, by definition, is going to be the integral from negative infinity to infinity, x of t e to the j omega naught t e to the negative j omega t dt, which can be rewritten as the integral from negative infinity to infinity, x of t e to the negative j times the quantity omega minus omega naught t dt, which by definition is equal to x of j times omega minus omega naught. So for example, if we have x of j omega equal to the rect of omega over 2 pi, then the inverse Fourier transform is x of t is equal to sinc of t. So now, what if we have the shifted x of j omega minus pi over 4, which equals to the rect of omega minus pi over 4 divided by 2 pi, then the inverse Fourier transform is e to the negative j pi over 4 times the sinc of t. And what you should start to see here is that there are lots of parallels between Fourier transforms and Laplace transforms, and some of these properties are very similar to the time shifting and frequency shifting for Laplace transforms. Based upon what we just learned about frequency shifting, we can now discuss the modulation property, which states that if g of t is equal to m of t cosine omega naught t, this is equal to 1/2 e to the negative j omega naught t m of t plus 1/2 e to the j omega naught t m of t. The Fourier transform is g of omega is equal to 1/2 m of j of omega minus omega naught plus 1/2 m of j of omega plus omega naught. So what we say here is that m of t is the message signal and m of j omega is the baseband spectrum. So suppose m of j omega has the following shape for the magnitude and for the phase. Then g of j omega, based upon the modulation property, would look like the following. It's going to be a copy of that signal at omega naught and at negative omega naught with an amplitude of k over 2, and the phase is also a copy that looks like the following. If omega naught is a high frequency radio transmission of g of t is possible. G of t is said to be a modulated signal, and cosine omega naught t is called the carrier. Our final property for today's lecture will be convolution. Convolution property states that if y of t is equal to x of t convolves with h of t, then y of j omega is equal to x of j omega times h of j omega. Once again, this is seen familiar from the time domain for Laplace transforms, where y of t convolved with x of t, y of t equal to x of t convolved with h of t was equal to y of s equal to x of s times h of s, where h of j omega was the frequency response, h of s is the transfer function. So, using the definition, we have y of j omega is equal to the integral from minus infinity to positive infinity, y of t e to the negative j omega t dt. So, using our definition of the convolution, we have the integral from minus infinity to infinity, the integral from minus infinity to infinity, x of tau, h of t minus tau, d tau, that's y of t, times e to the negative j omega t dt. This can be rewritten as the integral from minus infinity to infinity, the integral from minus infinity to infinity, x of tau, h of t minus tau, e to the negative j omega t, d tau dt. So rearranging, we have the integral from negative infinity to infinity, x of tau times the quantity, the integral from negative infinity to infinity, h of t minus tau, e to the negative j omega tau t dt, d tau. So now we're going to do a substitution. Let sigma equal t minus tau, which means that t equals sigma plus tau, and that d sigma equals dt. So using our variable substitution, we have the integral from negative infinity to infinity, x of tau times the quantity from negative infinity to infinity, h of sigma, e to the negative j omega sigma, d sigma, and e to the negative j omega tau, d tau. So now our integral becomes the integral from minus infinity to infinity, x of tau. The bracket is h of j omega, so I can write that as h of j omega, e to the negative j omega tau, d tau. Now I can pull out the h of j omega, so I have h of j omega times the integral from negative infinity to infinity, x of tau, e to the negative j omega tau, d tau. This second integral is x of j omega, so this can be written as h of j omega times x of j omega. So we have shown that convolution in a time domain becomes multiplication in the frequency domain. If you think about this symbolically, this means if I have a LTI system, h of t, where the input is x of t and the output is y of t, we know in the time domain that equals x of t convolved with h of t. And we now also know that in the frequency domain, I can represent that system as the frequency response h of j omega. And if the input is x of j omega, the output is y of j omega, which equals h of j omega times x of j omega. And this concludes lecture 5-3 on properties of Fourier transforms.